In this screencast, we're going to look at how to solve reactor design problems, just the mole balance part of those problems. And this is just an overview of the approach for ideal reactors, and then we'll provide links to more details for each of the type reactors and links to example problems that go through the actual calculations. So a few things that we want to keep in mind about most chemical reactors, and that affects the approach we're going to use to model these reactors, is that most reactors have multiple reactions taking place simultaneously. And the implication of this is that the calculations can become complicated, and we end up solving most of them numerically because we have a number of mole balances. Also, most, not all, but most reactors, large-scale reactors, are non-isothermal, which means we also have to write an energy balance. Because of these complications, most reactor models are going to be solved numerically. We can't get an analytical solution. So then, a couple important aspects, some things we need to keep in mind when we write down the mole balances for these reactors are the following. One is that we write mole balances on individual components. That is, we don't write just one mole balance for each reaction. So if we have 3 reactions, we have 3 mole balances. Instead, we might have 6 or 7 mole balances depending on how many components are in each of these reactions. So the mole balances are written on individual components. So if I have species A, B, and C, I'll write down a mole balance for A, another mole balance for B, and another mole balance for C. That is, we're writing one balance for each component. So let's look at the best variables to use when we write down these mole balances, and we'll do it for each of the ideal types of reactors, and then we'll look at what's the starting equation we should use for these mole balances. We'll start off with the batch reactor and also the semi-batch, because they really have a lot of similarities. And so the best variables to use are the number of moles of each species, and that's for the batch reactor. Also then, for semi-batch, we need to use the molar flow rate. So this is total number of moles, of course, in the reactor, and this is moles per time. And the general form then of the starting equation, say for component A, change in the number of moles of A respect to time, this accumulation term, is equal to the rate of reaction. That's for a batch reactor. For a semi-batch, we may have additional terms such as flow of A into the reactor or flow of A out. We may have one of these terms, we could have both of these terms. Or we could not have any flow in of A, but we might have flow of B into the reactor. For a continuous stirred tank reactor, we can certainly use the molar flow rates of A, but often, most cases, these are liquid phase, so using the concentration is also a reasonable variable. And the general mass balance for a steady state CSTR is a molar flow rate of N of A, the molar flow rate out, and then the rate of reaction times volume. And keep in mind this rate expression R sub A can be positive or negative depending on where A is a reactant or product. Third type of ideal reactor is a plug flow reactor. Here the best variable typically to use is the molar flow rate, and the typical form of the starting equation, again we're looking at steady state reactor, is to change in that molar flow rate as a function of cumulative volume is equal to the rate of reaction. So one thing to note, if we look at the equation just for the batch reactor, which is what I've circled, compared to a plug flow reactor, these equations are essentially of identical form, where the time spent in the batch reactor, the time we have available for reaction, corresponds to the time it takes to move through the plug flow reactor. So these equations are really quite similar and are solved essentially the same way. Now I've indicated the variables that we could use. Well, we could use fractional conversion. So fractional conversion is the flow rate of A in, for example, in a plug flow reactor, flow rate leaving over the flow rate in. Well, we could use this where this is the flow rate at any point in the reactor, and then that's the fractional conversion at any point. We could use this as our variable instead, and that works for the simple cases, but it does not work as soon as we introduce additional complications. If we have multiple reactions, for example, doesn't work. If we have a semi-batch reactor, that's not a good variable. If we look at the startup of a CSTR, we've indicated here the steady state equation, but if we look at the startup, and what's going to be different in startup is we'd have, instead of 0 on the left side of this equation, we have the change in the number of moles of A with respect to time in accumulation term. Or if we looked at a plug flow reactor where there's a side stream either entering or leaving, such as a membrane reactor, then we can't use conversion. So our general approach then to solving mole balances in reactors is, first we start with the mole balance and we write as many mole balances as we have species in the reactor. Next, we substitute into these equations for the rate of reaction. For example, if we had A goes to 2B and the rate of reaction is the rate constant times the concentration of A squared, there's a minus sign for A because it's reactant. The rate of B plus, and there's 2 for the stoichiometric coefficient. We would substitute these into the appropriate equation, keeping in mind the stoichiometric coefficients. The third thing then that we would do, if we have gas phase reactions, flow reactor, which is typically how we carry out gas phase reactions, we have to account for the fact that often the volumetric flow rate changes as we move through the reactor. For example, in a plug flow reactor, the volumetric flow rate changes because the temperature changes. As temperature changes, if you think of ideal gas law, then the volume, if temperature increases, the volume increases. If it's a packed bed reactor and the pressure is dropping, this means the gas expands, occupies more volume. This affects the concentration, therefore affects the rate of reaction. And then if we have mole change, so this reaction, A gas phase goes to 2B in the gas phase, this mole change is going to affect concentrations. As we move through the reactor, the concentration of A is decreasing because of reaction, but it's also decreasing because it's getting diluted by B, and this is going to slow down the reaction more than it would be otherwise, and we have to account for that. And so the way we account for this is if we write down, for example, we can use an equation state. I'll just write it for ideal gas equation state. The concentration is a function of pressure, temperature, ideal gas constant, and the mole fraction of A, which in a flow reactor we can write, for the simple case of just A and B present, the ratio flow rate of A over the flow rate of A plus B is the mole fraction of A, and then pressure over RT. So we use this for each of the components that we have in the rate expressions, and then the next thing we do is solve these equations numerically. Of course, this also makes it easy to change conditions and look at what happens. So keep in mind when we use concentrations, these are local concentrations in the reactor. What I mean by that, if we had a liquid phase reaction that forms a solid product, if we had A liquid goes to B solid, and the solid does not dissolve in the liquid, so it separates out or it's carried through in slurry form, then the concentration of A actually would not decrease as reaction took place, and this would affect the rate of reaction. And so in the screencast, we provided links for the various reactors that goes through details of where these mass balances came from and then how to use them in calculations. But here we're trying to give you an overview of writing mass balances for chemical reactors.